In this video, we'll discuss the third law of thermodynamics. We start with the basic law, which simply says that as the temperature approaches absolute zero, that's 0 kelvins, the entropy must approach zero. And that at absolute zero, the entropy will be zero for all perfectly crystalline substances. If we go back to the Boltzmann definition of entropy, where entropy is related to the natural log of W, W being the number of ways to configure a particular state, this third law would then indicate that at absolute zero, W would be equal to 1 for a perfectly crystalline substance, and that should make sense because for a perfectly crystalline substance there would be only one way to achieve that particular configuration. It's also important to note that in reality we cannot obtain absolute zero. We can improve the technology to the point where we can get closer and closer to absolute zero, but however we'll never be able to reach absolute zero. Now, since the third law says a perfectly crystalline substance would have an entropy of zero at absolute zero, we can then determine the entropy at temperatures above absolute zero by simply calculating based on experimental data. Here's a simple relationship here, and we'll talk about this in more detail on the next slide, that will allow us to obtain an entropy at some temperature above absolute zero. Remembering, of course, that the basic definition of entropy is dq over T, and that for a constant pressure process where we are changing the temperature, this simply becomes Cp dt over T. So if we want to determine the entropy at a particular temperature above absolute zero, realizing that the entropy at zero is equal to zero, we just simply do this integration as indicated here in this expression. So when we heat a substance as we go to temperatures above absolute zero, we simply do this integration to determine what the entropy change would be corresponding to that heating. And then if there's any phase change, for example, as we go from solid to liquid, liquid to vapor, then we must add the entropies associated with those transitions. Again, remembering for transitions, delta S is equal to delta H for that transition over T. Now, it is important to note that as you take a look at this, it's the third law entropy is given the symbol S, not delta S. This is not the entropy of formation. Just like when you look in these tables, of course, you'll find enthalpies of formation, delta H sub F, and you'll find Gibbs energies of formation, delta G sub F, but you will not find the tabulated values to be delta S. You'll instead find them to be S. And again, this is based on the third law. Those values that are given in the table assume that the entropy at absolute zero is equal to zero. Now, we want to calculate reactions. We can calculate reaction entropies the same way. We calculate delta H for a reaction, or we calculate delta G for a reaction. We simply use this expression where we take the third law entropies tabulated and we multiply them by the stoichiometric coefficient for the particular reaction, where of course these coefficients are negative for the reactants and positive for the products. So for this simple reaction given here, we'll note that again delta S is just products minus reactants, just as we always did when calculating delta H and delta G. Now let's look at how we might take experimental data to calculate the third law entropy for O2 at 298 Kelvin. In this diagram here, along the vertical axis, you have Cp over T plotted versus T along the horizontal axis. And you have it for all the phases of oxygen at 1 bar pressure that exist above 0 Kelvin. You'll notice there are actually 3 phases of oxygen that exist at 1 bar at 1 bar pressure. And we'll talk a little bit more about phases, different kinds of phases, later on in the semester. But it's important to note that there are 3 distinct phases as we go through this particular determination. Okay, so since we've plotted Cp over T versus T, the determination of the third law of entropy at 298 Kelvin involves these integrations that I talked about on the previous slide. And so the first one's going to be from 0 to 23.8 Kelvin, where we are for solid phase 3, we are taking the integral of Cp over T in that region indicated here for solid phase 3, from here to here. All right, and that's simply the area under the curve between 0 and 23.8 Kelvin. Then we note that solid 3 undergoes a phase transition to solid 2, so we must add to that the enthalpy change associated with that phase transition divided by the temperature, which occurs 23.8. The next step then involves taking a look at Cp over T, the area under the curve, between 23.8 and 43.8 kelvins. And again, we're integrating Cp over T dt over this temperature range. So once again, we'll note that's the area under the curve between those 2 temperatures. So again, the area under the curve of the Cp versus T is what we would determine in this integration. So then again, at 43.8 kelvins, of course, there's a transition from solid phase 2 to solid phase 1. So we need to add the entropy change corresponding to that particular transition, using the enthalpy change for that transition and, of course, the transition temperature. And then as we continue to go up the ladder of temperatures, we then are at solid phase 1, and we do the integration from 43.8 to 54.4, which is the melting point of solid phase 1. And again, the area under the curve in that region corresponds to the integration. And then it melts. And at the melting point, we add the enthalpy of fusion divided by the temperature. So there's the entropy of fusion associated with the transition from solid phase 1 to liquid oxygen at 54.4 kelvins. Continuing to go up in temperature from 54.4 to 90.2, which is the boiling point of liquid oxygen, we then again integrate, determine the area under the curve in that region, adding it to our entropy, followed by the entropy of vaporization at the boiling point, delta H vaporization plus over 90.2, and then finally it's vapor, and we continue to increase the temperature to our final temperature 298, since that's our target, determine the third law of entropy at 298 Kelvin, and we just very simply integrate the area under the curve for that region from 90.2, the boiling point, to 298. So there, when we add all these together, we get the third law entropy value, 402, that's tabulated at 298 Kelvin and 1 bar pressure. I didn't mention this, but these data are all collected at 1 bar pressure. So this is the standard third law entropy at 298 Kelvin of 205.2 joules per Kelvin per mole. So that's how we use experimental data to determine the third law entropy value at a specific temperature. This ends our discussion of third law entropies.